Okay, now we had a chat. Abraham is trying to get in. I don't see anyone trying to get in. Tom, try again because I haven't seen him try to get in as yet. So, going on, morning. We're going to start hydrostatics this morning. Hydrostatics comes from the broken up of two words. Let me just make sure my pens are working. Yep, pens are up and working. Good. All right. Hydrostatic comes from two words. All right. Hydro, which comes from the word for liquid, and static means for motion. All right, so basically we are looking at how water and gases move because they behave slightly differently than solids, hence why we have to put them in a category on their own. So reading from the screen, let's read from the screen. Hydrostatics is essentially the mechanics of fluids. Now, a fluid is categorized as a liquid and a gas, because when it comes down to the basic physics on liquids and gases, they're very, very similar to each other. So they're classified as one whole topic called fluids. All right, so reading on. All fluids are subject to gravity, meaning gravity does have some role to play on gravity as everything else on this planet. And this plays a big role in determining how they act. So you all have to know what pressure looks like. Our first topic here is pressure. We have pressure in both solids and fluids. All right, so let's read on pressure on solids. So pressure is defined as the amount of force that acts per unit area. So that's looking at the amount of force that is acting on some given area. That is what we mean by pressure. So let's look to see the formula for this. Pressure is equal to force over area. Nice, simple, sweet little equation. Pressure is equal to force over area, right? Please note that our units of pressure is the Pascal. And how do we work with Pascals? Just reading here, I always will give you the units if you all ever notice that. Anytime we do our equation, I will have the accompanying units. So pressure is equal to, if that's a bit tiny, let's zoom in a wee bit. Okay, that's too much. All right, pressure is equal to force over area. The units for force is the Newton, and units for area is meters squared. So the units for pressure is newtons per meter square, or a brand new topic, brand new unit called the Pascal. All right, so if you want, you could go and read up on the guy called Pascal. Pretty awesome scientists, as they all were, because they did multiple fields and multiple endeavors. Okay, so let's go on. Oops. I have no scroll button, so my thing is weird. So just remember, our first equation here is pressure is equal to force over area. Write that down in a little piece of paper somewhere because this is what we're going to be using today. All right, so our first equation for the day is pressure is equal to force over area. So continue reading. Generally, the largest and most obvious force on an object is its weight. It acts downward and will always act on the area that it is in contact, with the ground. Anybody could tell me how do we work out the weight of an object again? Anyone? You could put it in the chat or you could say it. Weight is what by what?
Mass by a value or something, sir.
Mass by what?
Mass by
Mass by Ra?
no something. Mass by something.
Obviously, it's mass by something. Anyone asking in the chat? Let's see. Nope, not mass over volume. It's mass by something. You're kind of close.
By gravity.
Mass by the acceleration due to gravity.
Yeah, miss, I'm not going to say that.
Right? So weight is equal to mass by gravity. This is something you should always remember. Anytime you deal with forces, please note when you're on Earth, you have a force already. And that force is called your weight. Your weight is a downward force that is a result of gravity. So we always have a force acting on us, and that is our weight. So let's continue. Let's read this again. Generally, the largest and most obvious force on an object is its weight. It acts downward and will act on the area that is in contact with the ground. So please note when you're standing up on the ground, as my stick figure, listen. Right? Your weight is what you have in contact with the ground. That is with the pressure you are exerting on the ground. So that's our two equations for the morning so far. Pressure is equal to force over area, and weight is equal to mass by gravity. And please note, weight is a force. All right, so let's continue. So I have here, let's think about this three-dimensionally, because we do live in a three-dimensional world, right? We have the weight of an object acts down, and the area that is in contact with the ground is where that force is acting. So let's take a look, continue reading. Factors that increase pressure are 1, increasing the weight or the force, and 2, decreasing the area which it is acting on. This is known as an inverse relationship. So let's see what this means. I think there's just questions from here. This is where we're going to use some thought exercises. All right, so if you have your calculator out, get them out. All right, or that's a little small, yeah, that small piece of paper. Let's say I have an object. All right, this object has a mass of 10 kilograms. Say this object has a mass of 10 kilograms and the entire weight of this object or the entire force of this object is acting on an area of 1 meter squared. I want us to work out the pressure that is being exerted on this area here. Remember, pressure is equal to force over area. And how do we work out force here? Force is also your mass by gravity over your area. Anybody wants to tell me what's the value of gravity that we use at the CSEC level again?
Miss 10.
10. Very good. Awesome. G is a nice, easy number at CSEC. At CAPE is a complicated 9.81. Right? But we have a very sweet number of 10. Right. So I know G is 10. I know the mass of my object is 10 kilograms also. Put in our units. I know my area is 1. I want to work out the force on this area that is 1 meter square. So that is going to be, force here is mass by gravity, 10 by 10 over 1, and that's going to give me 100. Everybody okay with that?
Yes.
Yeah?
Yeah.
So that's the first example. Let's look at a second one. Let me just get some space on the screen. Now, suppose in the same situation, right? My same object now is on a tiny little space, and my area is now 0.02 meters square. I want us to work out the force, the pressure that is on this little tiny space here. All right, so how we working out pressure? Pressure is equal to force over area, which is equal to your mass by gravity over your area. Anybody wants to give that a try quick? All right, it's the same mass and the same gravity, it's just the area is now different. Give it a try. Tell me what you get.
Miss, is it possible to get 5,000?
It is very possible to get 5,000. Anybody else got 5,000?
Yep.
All right, you all can give me thumbs up, so I will see the thumbs up and reactions. Give me thumbs up. Good. 2 thumbs up, 3 thumbs up. We're going, yes, man. That's what we're talking about. All right. So this is what we mean by an inverse relationship, all right? Because let's get a clear board again. Pressure is equal to force over area. There are 2 ways you can increase the pressure in something. One, you can increase the force. That's obvious. Obviously, if you put a bigger force, you're going to get a greater pressure, because what is pressure? Pressure is simply a force acting on a given area. Think about it, right? We're going to do some simple little demonstration just now. All right, simply force acting on an area. So one way to increase your pressure is to increase a force. And we saw just now, we can decrease the area. Everybody, what I want you to do for me right now is to take, say, like the back of your pen. Let me see if I have my video up. Oh, why is it blurry? Okay, anyway. All right, stop share. Speaker. Wow, that is blurry. Hold on. Anyway, everybody, with a pen. All right, I want you all on your hand to take the dull side of your pen and kind of press it on your hand. The area here is kind of bigger to the next side. Let's press it on your hand. You're going to feel the pressure of the pen on your hand. But now use the pointy side, which has a smaller area than the bottom of your pen. All right, and you're going to actually feel that it kind of hurts. Now, don't poke yourself so much at your break skin. That is your own fault, not mine. All right, you all see any difference? And actually you can see the little indentations, all right, in your hand just by poking with the pencil point or the sharp point. All right, so this is where area makes a difference in pressure. Pressure is simply how much force we have acting on a given area. All right, so if I take a large pressure, a large area, all right, something large, and press it on my hand, I'm not going to feel much. All right, I can press much, and you all can take something large and press really hard on your hand, right? To the point where I'm bending my finger at weird angles. If I try that with my pencil and press it so hard that I'm bending my finger, ow, that's going to really hurt. Why? Because pressure tells us how much force is acting over an area. And the smaller your area, the larger the pressure is concentrated, or the larger the force acts. Everybody get that? Everybody tried it and poked themselves with a pencil and pen?
Yes, ma'am.
Yes.
Good. All right, so let's go back to the share screen. All right, another way of seeing this is, ladies, we all have heels, right? Some of us wear heels, right? You all ever try to walk on soft ground?
Not good.
Not good. It's never good trying to walk on soft ground. You ever notice, like in sand? Guys too, right? Next time your family goes to a church outing that's out in the field or by the ground, or a wedding or something, you're going to notice these ladies and their heels create little holes in the sand, right? But if you look at the guys next to them, you're just going to notice just a really light little imprint with their shoes. Right? You all ever notice that?
Yes, ma'am.
Yeah.
Yes, yes,
Why is
yes.
that? That has nothing to do with your weight, right? Because a heavy person could walk with a regular shoes and they'll leave a really light little imprint in the sand or in the dirt or in the pitch. But a lady with a high heel shoes could be a little teeny tiny somebody and they could walk on the in that soft material with the high heel shoes, and these shoes are going to go straight down into the soft material. Why? Because the pressure is greater due to the small area, right? Pressure tells us how much force is acting per unit area. So the smaller area, the greater the pressure is exerted, right? So you all have to remember what are the two ways to increase pressure? One, by increasing your force, and two, by decreasing your area. So let's continue going. So we have some questions here to try. You all will give this a try a little later on since it's there. All right, so I will put up the solutions a little later, but you all can give these questions a try. All right, they're not hard. Some of them is actually kind of self-explanatory. Pressure is equal to force over area. I know my force is 100 newtons. And we're going to have our areas. I'm just going to guide you all here. This is easy. This is easy. Divide by the two numbers. I have C 40,000 cm squared. Please know that the area must be measured in meters squared. So cm squared will not work. So what do we do when we encounter cm squared? We have to convert it. I think I would have given you conversion sometime before in term one. All right, but that's to recall, write it down somewhere, right? 1 meter squared is equal to 10,000 centimeters square. You all remember doing this when I did the square and the box with the 1 meter by 1 meter?
Yeah, miss.
Right? So if you want to do, you can get 1 cm square is equal to 1 divided by 10,000 meters square. So anytime you want to convert from cm square to meter square, all you have to do is divide by 1,000. So if you want, in simple notes, cm square to meter square, you divide by 10,000. Write that down. Make sure and write that down and remember them. Right? It should be in your notes from term one. All right, but that's, for quick reference when you're doing this, going to try these questions. So I have here 40,000. You have to convert them to meters. Area must be in meters square. D, 20 cm by 1 meter. This is where I have uneven units. I have a meter by centimeters. So you're going to have to convert this 20 centimeters into meters. How do we convert cm to meters? Again, we divide by, are listening? How do we convert centimeters to meters? We divide by 10,000. No, that's cm square.
100.
100. Right? You divide by 100. So cm to meters, you divide by 100. Right? So you convert this to meters first, and then you move on. And then I have here, let me see if anybody can figure this out. Radius of 7 centimeters. How am I finding? Is this my area? Yes or no?
Yes.
Radius is a area.
No, boy.
What type of shape has a radius?
A circle.
A circle. How do you find the area of a circle?
2 pi r.
No.
It's pi r squared.
Pi r squared. You know, things that you learn in Form 1 or in primary school. All right, so what you had to do here was to convert this to meters first, all right? And then work out your area using pi r squared. Folks, please, 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 please do not use 22/7 when you're working out these things. Don't use it. You have a pi button. Please use it. My wonderful Sharon, please, please use the pi button on your calculator. 22/7, we don't need to use it in physics because you're allowed to use your calculator in every single physics exam. All right, so moving on. So y'all can give those a trial later. This is a similar one. If a container has an area of 50,000 cm squared, how much pressure would act if it had a weight of 50 newtons? So this you'd have to convert it. All right, same thing like the previous question. Question 3, a cuboid has the dimensions of, we're going to see there, all right, of A, B, C. Determine which face will have the smallest pressure on it. So our faces here are A, all right, then we have B, and let me get a silver pen, all right, and then we have C. All right, we have 3 different faces, and this is where we have to go and work out the areas of our 3 faces.
Miss B
Right?
go add the
Say that again?
B, miss.
They have no D. The question only has, in a cuboid, we have 3 faces multiplied by 2. Because
Miss
this
B go
face
add the
here,
small first time.
yeah, A is the same thing at the bottom here. All right, C face is the same face in the back here. And B, let me get 51. And B face, which is this face, is this same face here. So when you have a cuboid, it's the same faces times 2. So what you're going to do for a question like this, you're going to work out 1, the area of each face. All right, so the area of A, now if you look at here, A has a length, well, a breadth of 3. Woo! Sorry. That's when I touch the drawing pad with. Right? Has a width of 3 and a length of, anybody wants to tell me what's the length of A?
4.
4. So you can say A is equal to 0.03 multiplied 0.04. Anybody wants to know why I'm using 0.03 and not 3?
Because you want to use meters.
Because of what?
Because you're using meters.
Good, very good. Remember, you have to use meters. So you have to convert your centimeters. So you find the area of A. Then you're going to find the area of B. Anybody want to tell me what's the area? What is the sides for B? What by what?
Zero 0.04 multiplied by 0.05.
Very good. So you all will work that out. And C.
0.03 multiplied by 0.05.
Right? So we can see that C, right? This is C and this is for C. So it's 0.03 multiplied by 0.05. Right? All these lines here are 0.05. So you work out your areas for each one, guys and gals, and you will tell me which one will have the smallest pressure. Let me just give you the mass. Has $20 newtons. I'll put the correction on the board, on the handout. All right, so you all can give these a try. All right, pressure in liquids. This one is a little bit more. All right, so let's just see what we have. Trying to get, yeah. That'll work. Right? So pressure in liquids. First we did solids, and then we have to do pressure in liquids because we are very, very reliant on the pressure of liquids. Without the pressure of liquids, we wouldn't be able to live. As funny as that sounds, we're going to go through why that happened just now. So pressure in liquids. Liquids behave very differently to solids. You all can take a solid object and squeeze it, right? You can apply pressure in all directions, right? So a solid. What happens if you put your hand on water, if you try to squeeze water? Won't your hand just go through the water?
Yes, yes.
Yeah? Suppose all they have a water balloon. What's going to happen if you try to squeeze a water balloon? It could pop, but it'll just be kind of squishy and move away from your hand, right? It goes in all kind of different directions. I don't even have a balloon to demonstrate. All right? We should get some water balloons for scientific inquiry in school and all, yeah?
Let's go to younger people. Yes, yes, we should.
No, we're going to demonstrate the strength and the action of pressure in liquids. I don't think we'll get permission. I could try. All right, so continue reading. Liquids have behave quite differently to solids, but they do exert a pressure. If anybody here swims, anybody here dives, they know that you do feel pressure on you when you go in water. All right? Anybody here who's been in a plane, anybody here who's gone up a kind of highish mountain, know that air pressure, you feel the air pressure in your ears. All right, so we do experience and we can experience air pressure and liquid pressure or fluid pressure. So let's continue reading. In fact, the very nature of liquids mean that okay, I give up. That they exert pressures in any direction. So this is one thing you have to learn about pressures in liquids. They are exerted in any direction. Different to pressure due to solids. Why pressure due to solids are different? Because the pressure acts downward. Why does it act downward? Because of weight, right? Weight and gravity acts downward. So that is for solids. Our pressure is going to act downwards. But in liquids, it's a little different. They act in every direction possible. They exert pressures in any direction. Because again, think about it as a water balloon. If you were to squeeze that water balloon from any direction, you're going to feel the pressure of that water from any direction that you squeeze it. So we have to know the derivation. You don't have to know the derivation at CSEC, so I'm not going to go through this with you. I'm just going to show you the formula. All right, but if anybody here wants to go through it, you're welcome to. Pressure in a liquid is given by the equation of rho GH, where rho is your density. Remember, I taught you how to write then rho. Rho is like take a E and stretch it out. That's rho, it's a Greek letter. We have the acceleration due to gravity, which is nice and sweet, 10 meters per second squared. And height is the depth below your surface. So that means the deeper you go in a liquid, the more pressure you would feel. Now, why is this happening? Let's think about this from common sense. Sorry. Do I have a diagram? Yeah, man, I have a diagram. If I have a small amount of water, let's say these are a small tray of water. All right, everybody here can lift up a tray of water. Like I say it's about 20 centimeters by 10 centimeters. No, let's say 30. You can lift up a tray of water like this. It's not going to be too heavy. All right. But say now I go and I get a bigger tray. All right. And I take a big container and say it's 30 centimeters by 30 centimeters. All right. Let's think about it. If you try to lift a container that's 30 cm by 30 cm, with water, that's going to be heavy. You'll know how heavy a bucket of water is. And a bucket is about 30 centimeters high. Yeah, about. Yeah, the black buckets we have home is about 30 centimeters high. And you try to lift that up full of water, it's pretty heavy. If anybody here tries to go and lift up a container of water that is 50 centimeters high, you're all in problems. It's going to be really, really heavy. So you try to lift up something that is 30 centimeters at the back, right? And 50 cm high. That's a lot of water, right? So you fill this up with water. Right? This is going to be very, very heavy. Why? Because water has a weight. And we are able to determine the weight of the water by the amount of water that there is. All right, so the more water we have, the greater the weight. And obviously, if the weight is greater, the pressure is going to be greater. Remember, pressure is equal to force over area. So using that little bit of knowledge, right? Let's think about this. If I have do I have a 3D shape? Yes. So I have a 3-dimensional shape. I see a chat. Yes, your back will break, Rena. All right. Say I have a big container of water, deep container of water, very, very big container, like a big barrel, a big tank, and this is 2 meters high. All right. It is filled with water. This is the surface of the water, and you go down to like right here. Let me get a survey. How many of y'all can swim? Give me a thumbs up. Swim okay enough. All right. Okay, that's good enough. All right. Those of you all can swim, you all know if you just put your head or go under the water a little bit, you're gonna feel the pressure on your, like your ears and your nose, but not so much. But say you go down to like a meter depth, 1 meter in depth, you're gonna feel some sort of pressure on you. Say you dive down to 2 meters. Those of you all could really swim and go down to 2 meters. You'll really, really feel your ears starting to hurt, right? And you'll probably feel some of the pressure building up in your nose. Anybody ever notice that?
Yes.
Yeah?
Yes.
Right?
Yeah.
Why? That is because the force of all that water is acting on you. And let's blow your mind here on how much that force is. All right? Get your calculators out. We know the density of water is 1,000 kilograms per meter cube. So that means, let me just tell you all, let's blow our minds a little bit. If I take a box that is 1 meter by 1 meter by 1 meter, which is 1 meter cube, the mass of the water inside of that box that is 1 meter cube is 1,000 kilograms. So if you all get a box, like a big box, a big square box that has like a washing machine or less than a washing machine, smaller than a washing machine box, and you fill that up with water, you get a box that could hold that amount of water, that is over 1,000 kilograms of water. That's a ton of water. All right, that is how heavy water is. So if you go down 2 meters, guess what? You now have 2,000 kilograms of water acting on the very bottom of this area. Oh gosh, that'll work. You now have on this base here, 2,000 kilograms of water is acting on the base here. That is how heavy water is. That is why water is so destructive, right? Because it's very heavy. It's very easy to move, and it's very, very, very heavy, right? Hence why if you all put like a full bottle of water in your bag gets heavy. If you have no water in that bottle of water, it's a light bag because water does have a significant amount of weight to it. Right? So this is why as you go down deeper in water, the pressure is going to get larger and larger. When you go shallow, because you only have a little bit of water acting on you, your pressure is going to be small. But the deeper you go, your pressure is going to get larger because you have the weight of more water acting on you. Everybody understands that?
Yes.
Yeah?
Yes.
Okay. So this is why when you dive, or even for divers, they can't go too deep because it's going to be dangerous on them, right? Or they have to learn to exhale very slowly, or they have to learn to take their time, right, when coming back up, because coming out of water that is very deep will kill you. All right, many things can kill you in this world. All right. So we have here for pressures in a liquid, this is in your solid, this is in your liquid, is rho by gravity by height. And your height here is actually depth below your surface, right? If I have here, when I'm working out pressure questions, I want how far we are from the surface. That is going to tell you how much pressure is being exerted on an object or a system. How far it is from the base makes absolutely no difference. You need to know how far it is from the top. So make sure, remember that, make sure, note that. Anytime you're doing pressure questions, you're looking at the distance from the surface, not the distance from the base. Because you know questions are going to have, some questions are going to have you looking at from the base or trying to tie you up. Like in the next question, right, I have right at the bottom. So please remember that your depths are always measured from your surface. So continuing on. So we have here, so let's determine the pressure at depths of 5 meters, 10 meters, 10 kilometers, and our pressure equation is rho GH, right? Where the density of water is 1,000 kilograms per meter cube, and gravity is equal to 10. So you all can go and give these a quick workout. Chat. 11:30, I'll see where we reach it. All right. Now, if anybody has to leave early, all right, I want to see between 11 and 11:30 because I usually stop at a certain topic. I don't stop in between. All right. So if I realize I reach a topic that I can stop at, I will stop there. All right. But again, if anyone has to leave, the session is being recorded. Is it being recorded? Yeah, it is being recorded, so you can always look at it again. All right, so for these questions here, let's work out the pressure, considering you know what your density is, you know what gravity is, just multiply by height. These are multiplying and nothing here is adding or subtracting. All right, I have a next question here, which is a combination of units. All right, in the diagram below, determine the pressure depths A, B, and C. right? Our density is 1,000 kilograms per meter cube. That is the density of water. So I have 1A is 4.5. C is at the bottom, and I already gave you the distance to the bottom. And no, B is at the bottom, and C is 300 centimeters below A. So you kind of have to add some numbers and stuff. All right, any questions before I move on? Everyone okay? We okay with anything right now? Any questions on anything you want me to go back to right now? Okay, we're looking good. Everybody else all right? Thumbs up, thumbs down. You could give me a sleepy face. Give me a sad face. Let's get everything in here. Okay, moving on. Properties of liquids. All right, this one we're gonna have to do in school because you'll have to write a diagram, draw something, and this is something I don't want you to just read. So properties of liquids to do in school. But I could send you a little short handout on this chat. Okay. All right, hydraulic principle. Again, we'll do this in school. I want to go straight on to atmospheric pressure. We'll do atmospheric pressure, start barometers, and then we will wrap up. So whatever time we do that, we'll finish. Atmospheric pressure, some of you all are doing geography. Or everyone here would have done geography until Form 3. And I am pretty sure you've heard of the term atmospheric pressure before. Right? And atmospheric pressure is an extremely, extremely important quantity to know and appreciate. So let's read. The Earth's atmosphere extends up nearly 100 kilometers straight up. The Earth's atmosphere is really thin compared to the rest of the Earth, but it's the part of the Earth that we live in. The majority of the air lies within 17 kilometers of the surface. All right, I am telling you, if you all go beyond 10 kilometers up in the atmosphere, you are going to have a very hard time breathing. All right, Mount Everest is 8 kilometers, I think. 9 kilometers, and most of the climbers who go at the top there need to carry supplemental oxygen in order to breathe. All right, so we don't have too much breathable air, right, above us, but we do have a lot of air. If you recall, all right, 70% of our air is made up of what? Chemistry and bio students, let me hear all you. Anybody know what 70% of our atmosphere is made up of? I see in a chat.
That's oxygen.
No.
Yes.
70% of our. Say that
That's
again?
oxygen.
Wrong.
Is it nitrogen?
Nitrogen. 70% of our atmosphere is made up of nitrogen. 20% of our atmosphere is made up of oxygen. And the other 10 are small inert gases, carbon dioxide, other greenhouse gases. All right, so 70% of our air is nitrogen. All right, and our body actually is built to handle that amount of nitrogen. All right, nitrogen doesn't really do us much because, again, look, we're mainly breathing nitrogen, but our bodies are built to take in oxygen and harness oxygen for respiration. So continue reading. All of this air will exert a force on the surface of the earth, thus giving us a pressure. This pressure exerted by air is called atmospheric pressure. Let's see. All right, let's think about this a little bit. If this is my surface of the earth, and I have 10 kilometers of air, the density of air, all there is 1 kilogram per meter cube. 1 kilogram per meter cube. All right? Anybody who wants to work out what's the pressure exerted? Oh, that's here. If I had 10 kilometers of air, that's going to be 10,000 meters of air. If my density is 1 kilogram, then that means the force exerted by 10 kilometers of air is 10,000 newtons, or wait, that's not right. Don't tell me wrong here. Force pressure. GH will be 1 by 10 by 10,000, which is 100,000 pascals. On the earth, we have 100,000 pascals of air acting on every meter square. If you wanted to put that down on every single meter on this planet, 1 meter square, you have 10,000 newtons of force acting. Let me just erase this. You can work it out. We'll work it out in class properly. On every single meter square on the surface of this planet, you have 10,000 newtons of force acting on it. So that means on you right now, if you were to take up a space of 1 meter square, you have 10,000 newtons acting on every single part of this planet. We are built to handle this pressure. Air pressure is a significant number. It's not a small number, right? It's a significant number to look at, and we're going to see why air pressure is important and how we are built to handle air pressure. So continue reading. Let's read it back again. The pressure exerted by air is called atmospheric pressure. This is actually going to come up in your multiple choice, your paper ones. Define what is meant by air pressure. Air pressure is the pressure exerted by the atmosphere or the air. We use sea level as an average point because the majority of our planet is water. So we take a reference point at sea level. So the atmospheric pressure, the average atmospheric pressure at sea level, and you will have to learn this value, is 1.01 by 10 to the 5 pascals. 1.01 by 10 to the 5 pascals. See why I taught you all to use standard form in a calculator? All right, so 1.01 by 10 to the 5 pascals, this is the average atmospheric pressure at sea level. Let's continue reading. Who's playing loud music? All right, so we use sea level as a reference point since more than 50% of the Earth is ocean. So let's just look at how pressure varies on our planet. We have our average sea level, that's our dotted line. So this is sea. I'm going to put blue for sea. All right, this is our sea. All right, we have land with trees. We don't really have so much trees again, you know. All right, we have hills, we have depressions. Depressions are areas that are below sea level but are on land. So average atmospheric pressure at sea level is 1.01 by 10 to the 5 pascals. Now, let me see if I can get your opinion or your kind of semi-educated guesses on where pressures and how pressures are going to vary. We just said that pressure is equal to rho GH. where H is the depth from your surface. Or in this case, our depth or our thickness of our atmosphere. All right, remember atmosphere is measured, this is the Earth, your atmosphere is a very thin layer from outside. All right, and this is the atmospheric pressure on us. So using that little bit of knowledge, is the atmospheric pressure at the top of a mountain going to be greater or less than 1.01 by 10 to the 5 pascals? Let's take a poll. Give me thumbs up if you think it's more than 1.01 by 10 to the 5 at the top of the mountain. Give me thumbs down if you think it's less. I give a big hint there just now. Thumbs up if you think it is more. Thumbs down if you think it's less. Only 3 people? I've seen some correct answers and seen some equally wrong answers. I've seen some confused people. All right, confused people. Let's think about this. Is atmospheric pressure at the top of a mountain more or less than 1.01 by 10 to the 5? If I were to have the Earth, remember I said pressure is equal to rho GH. Rho is constant, G is constant, H is what is making our difference. All right, so this is the surface of my planet. This is the top of my atmosphere. This is, let's get green. This is my mountain. Obviously, it's not to scale. And this is my distance to the surface, which is 1.01 by 10 to the 5 pascals. And this is the distance from the top of my atmosphere to the top of the mountain. Is this distance greater or less than to the surface of the Earth? Let's say that again. Is the distance from the top of the atmosphere to the top of the mountain smaller or greater than the distance from the top of the atmosphere to the surface of the Earth? It is less. You all, I drew it intentionally so you can see it is less. So if the H is less, and you know pressure is equal to rho GH, that means that the pressure at the top of the mountain is, why? Because there's physically less air acting on you at the top of a high mountain than not even a high mountain, than the amount of air on top of you on the surface of the land. Personal experience. Everybody here who's ever been in a plane, you all notice you have the effect of your ears popping, correct?
Yeah, ma'am.
Yeah? Those of us who've been in planes, you've noticed the effect or the phenomenon of having your ears pop. Your ears pop because the air pressure is changing. They do have to pressurize the airplane so that it's comfortable for you. But while you're rising, air pressure is dropping, and you notice the pop in your ears. Anybody here ever went up one of the higher hills in Trinidad and noticed you felt something similar in your ears?
Yes, ma'am.
Yeah. Personally, y'all, when we're driving up Lady Young Road, I start to feel my ears popping. When I go on the bigger hikes like Paria, the hike to Paria, or going up the highest mountain, going up to Paria in the North Coast, I will feel my ears pop. So it has nothing to do with speed. It just has, the fact that I'm going higher up. And not even that high up. It's probably a few hundred meters up. All right, nothing too horrible to talk about. You feel the difference in your ears. So this is my little advice to you, or just pay attention. All right, next time you all drive up a kind of higher hill in Trinidad, and the faster you do it, the better too. Notice if you start to feel like a little kind of cloggy feeling, like a clog feeling in your ears. All right, some people actually do feel a pop. All right, like a little pop in your ears, but some people feel like a clog feeling. That is because you are responding to the changes in air pressure. All right, because our ears has something called an eardrum. And our eardrum is a very, very, very thin, nearly translucent membrane that vibrates back to and fro. Right? And the change in air pressure is going to cause it to kind of vibrate a little bit further in and give you this little weird cloggy feeling. So pay attention next time. It's not always in a plane. You can notice it. That's if your ears are sensitive to it, you can pick it up. I can actually feel when the air pressure in the air due to storms are blowing in. Like if you have a really, really quick storm where the place gets dark really quickly, and thunder and lightning, I can feel the air pressure in my ears change. Take a look, take a listen and feel. Right? Our bodies are built to pay attention to the world. We just don't do it often. So back to here. At the top of a mountain, your air pressure is going to be less. It's probably going to be about 0.9 something by 10 to the 5. Now, I have here a depression. A depression is an area on the earth that is deeper than sea level. So it's like a deep area. Going back to this general reference, if this is the top of my atmosphere, this was a mountain, and let's say this is a little depression. Let's see if you all can rationalize all this. Do you think at the bottom of a depression, right, is the air pressure going to be greater or less at the bottom of a depression? Is it going to be greater than 1.01 by 10 to the 5? Or is it going to be less than 1.01 by 10 to the 5? It's going to be what? Say it again.
Greater.
It will be greater. Why? Because we have more air. Literally, we have more air acting on us, so the pressure is greater. The weight of the air on us is greater. And let's go even further than that. Say now I have a deep trench under the sea. This is our sea. If we were to go deep underwater, not even too deep underwater, we have two things acting on us. We have the pressure due to air, and then we have the pressure due to water. And water is 1,000 times heavier than air. All right? So the deeper you go in water, the far greater pressure you are going to experience. So when you go deep underwater, right, you feel a large amount of pressure. All right, if people go too deep in water without enough proper precautions, their eardrums will rupture. Right, their eyes can rupture. It gets pretty gross or pretty graphic. Right, and we have the flip side when we go into space. All right, I'll tell you about that just now. So, regular, let's take back this whole thing what we meant. At sea level, our pressure is 1.01 by 10 to the 5. If we go up, our air pressure is going to decrease. If we go deep below sea level or under sea level on land, our pressure is going to increase. And when we're underwater, we have the pressure of two things acting on us, the air pressure and the water pressure. But because the water pressure is so huge, we just look at water pressure. Since we just looked at it here, we talked that average atmospheric pressure is 1.01 by 10 to the 5. We use this value to represent something. So since there's an average atmospheric pressure, we can use this number to define a new unit. Please note this is not an SI unit, so you cannot use it in calculations generally, right? But we do use it sometimes. So we have a new unit to look at, and this is called an atmosphere. An atmosphere is ATM, it is abbreviated to ATM. So 1 ATM is equal to 1.01 by 10 to the 5 Pascal. So rather than writing on this value, I can say something is 1 ATM. I can say something is 1.5 ATMs. All right, I can say something is 0.9 ATMs. All right, this simply tells us this number multiplied by this value. All right, because this is a general accepted value across the planet. All right, so we use it to define a new unit to make it convenient. All right, but please note we don't use it in calculations generally. Sometimes we can. Please note that this is not an SI unit. As I said, this is not an SI unit. So when performing calculations, it is necessary to convert to pascals unless otherwise stated. So let's see how we do that. Write down a note for that conversion. 1 atmosphere, we got the pen. All right, 1 atmosphere is equal to 1.01 by 10 to the 5 pascals. And I can write down 1 Pascal is equal to 1 divided by 1.01 by 10 to the 5 atmospheres. So if I want to do my conversion, this is what we do. From pascals to atmospheres, we divide by 1.01 by 10 to the 5, and vice versa, atmospheres to pascals, we multiply by 1.01 by 10 to the 5. You want to write it down? You write it down quick. All right, so this is just another convenient way of writing down values. When we're doing calculations that involves SI units, you will have to convert them. But it just makes it, a little more convenient to write. But my personal advice to you, the instant you see ATM anywhere, please convert it to pascals. Whether they ask you or not, just jot it down in the corner somewhere to convert it. All right, and I will wrap up this now. I will stop at measuring atmospheric pressure with the barometer because this takes a little while. This takes some maths to do. All right, it's more than this. All right, let me just give you a little gory details on life in big and small pressures. All right, and why blood pressure is important to people. We all know that in space there is no air. We all know that, right? I hope everybody knows that. I don't assume anything anymore. No, we have a blue planet. Let's do a blue planet. All right, we have a blue and green planet where we have atmospheric pressure. When we go out into space, there is no air. When there is no air, this means that we also have no air pressure. No air pressure meaning 0 air pressure. And this is something something that they don't see in movies too often. When you go out in somewhere that has no air pressure, bad things happen to the human body. Very, very bad things. When you go in an area that has very low pressure, very, very, very horrible things happen. Why? Because in our bloodstream, we have a pressure that keeps our blood flowing, right? It's not just a velocity. You need the pressure to push it through the body, right? You need to push this blood through the body, and it moves through all our veins, all our arteries, all our fine capillaries, everything in your body. Now, this pressure is built to handle generally 1.01 by 10 to the 5. It is meant to be regularized with our air pressure on the planet. We can take a little bit of more, we can take a little bit of less. But if we take plenty less, something is going to happen. Why? Because what happens when you have too much air, too little bit of air pressure, right? That means we are going to have a buildup of pressure in your veins. And you know what's going to happen if we go into somewhere that has no air pressure? What's going to happen? Anyone want to guess what this means?
You must say blood gone burst through your fingertip, something.
Yep. It explodes out of all your extremities. So whatever areas of your body has the smallest surface areas, it generally explodes through there. So like your fingers, your ears, your eyes, your nose, your toes, right? It will explode through there. Generally explodes through your head. Right? Why? Because your head is a big ball of bone, and bone doesn't expand. So it reaches a point where it just shatters. All right, so this is what happens if you go without protective gear out into space. You can explode, but the problem is space is very, very, very cold. And it is likely you will freeze before you explode.
Miss,
Yes.
I have a question.
Uh-huh.
So, anybody died to like prove this, or it's just something to expect?
No, well, they have machines down on Earth where they can reduce the pressure. You can take a big chamber and drop the pressure, suck out all the air. Right? Remember, pressure has nothing to do with gravity. It simply has the air acting, the force of the air acting on something. So if you take out all of the air from something, right, you are going to make the blood pressure have nothing to go against, and it will explode. So they tested this on Earth already. They had to test everything on Earth. They needed to test what weightlessness did to bodies, what air pressure did to bodies, what is the range of air pressures that the human body can take. Right? So they tested it with everything. I think with zero air pressures, they tested like systems that, yeah, they did test live objects, not people though. Well, I don't know if they test people because humans are horrible, right? But they tested on a whole bunch of materials to see what zero pressure did and what large pressures did. All right, large pressures will tend to crush things, right? But it doesn't crush it into a big, into dust or into a liquid. It just remains by itself, where they crush everything. They crush the mechanism by which blood flows and whatnot. But when they go out into space, they have chambers that they reduce the pressure. Right? Anybody here ever heard of a hyperbaric chamber? Yes. Right? Hyperbaric chambers are chambers that they pump full with oxygen to change the air pressure around like a diver to help them heal from pressure wounds. From something called bends. If you want this, you'll read up today what the bends are. Read up what bends are. It's a horrible, horrible, horrible thing. Right? It's something that divers experience, deep sea divers experience. Right? And hyperbaric chambers are used for far more now. It's usually used to to flood a body with oxygen for healing purposes, right? And pressure purposes. A hyperbaric chamber is basically something that changes the pressure while the pressure outside is still normal and it doesn't affect them. But there is the extreme version where they can take a chamber and suck out all the air. And by sucking out all the air, we've depleted the air pressure, and it now becomes 0. There's no on this earth that we can reduce the gravity, but we can counteract gravity on the earth, but we'll do that the next day. All right, but in space, we will freeze before we explode because space is so cold. That's why Yondu froze Guardians of the Galaxy 2. That was 2, right? Or 3? 2. All right, they tend to freeze before they can explode because it's that cold. All right, so let's just review what we did today and then we'll wrap up. Hydrostatics, physics, mechanics of liquids. We have generally fluids are counted as liquids, liquid and gases. We have pressure and solid. Pressure and solid is given by simple equation, force over area. That's our first equation for today. Then we have, please note that a force is always mass by gravity. Always remember, once you have a mass and you're on this planet, you have a weight, and that means that you also have a force. All right. We have two methods by which we can increase our pressure, we can increase our force, and we can decrease the area because it's an inverse relationship. Please give the questions a try. They are in the handouts online already. Pressure in liquids is given by pressure is equal to rho, GH, where rho is the density of your fluid, G is the acceleration due to gravity, which is 10 for our use, and H is the distance below your surface, or how further down you go in your liquid. We have your various questions, and then we go through atmospheric pressure. Atmospheric pressure is simply the pressure exerted by the atmosphere on the surface of the earth. The average atmospheric pressure is 1.01 by 10 to the 5 pascals. All right, you have to know where pressure is larger and smaller. Just remember, atmospheric pressure means we're looking at the amount of air acting on an object. So the more air, the greater the pressure. The less air, the less the pressure. All right. Atmospheres can be taken as a brand new unit, but it is not an SI unit, so please don't use them for calculations. And know how to do your conversion. Next time I see you, or if you want to have a next class in this, we can have a next online session. Right. So we have atmospheric pressure, how to measure atmospheric pressure. You all can give this a read up. Obviously, there's more notes in here, right, to put in, just like a calculation. We have a manometer. We'll go through that. This is where we have calculations, but not too much. And then we're going to go into Archimedes' principle, floating and sinking. And we finish with this topic of hydrostatics. Oh, and you have a little piece here to do with hydraulic machines. All right, so let me stop the share and stop the record. So I'll wrap up the recording here.